Hey guys, my name is Osama Samara, and in this video we're gonna learn about shear joints. So in this figure represents uh, a group of shear joints. These joints can be pins, rivets, or bolts, and we're trying to analyze the shear stress on them. If you load the bar with an eccentric load. Right, so first things first, we have to locate the centroid of this uh, group of bolts. And in order to do so, you can use these two formulas, just like in statics, where you have to locate the centroid of an object. You basically just follow the formula. You have a1 right here times x1. So you're going from the origin to the centroid of the bolt or pin, and you continue to the, like for the second one, a1, this one, times x2, which is the distance from the origin to point 2. So like that. So this is your x2. And x3, same thing, and so on. And to find the y bar, the y coordinate of the centroid, same thing, but instead you're going in the y direction. Now you're going in the y direction instead of the x direction. Right, so we learned this formula in statics. So the main thing in this section, we have to find two main shear forces, right? So you have shear force, let's write that down. First one is the primary shear, which is called F prime, is gonna be equal to the shear force applied on these bolts divided by the number of bolts. So each bolt or rivet or pin will experience this primary shear. And the second one is called the secondary shear. So secondary shear, and it's governed by this formula. It's going to be equal to m, which is the moment applied on these group of bolts, times rn, n being the location of interest, or the bolt on which you're trying to find the secondary shear. Ra squared plus Rb squared plus Rc squared, and so on. Right, and you might be wondering, okay, so what is Ra? So let me draw a different. What is this one? What is Ra? And what is Rb? Same thing. What is Rc? Right, and this is just the Ra is just the distance from the centroid G of these bolts to bolt A, or to pin A. So this is your Ra. Right, and same thing for, let's go for Rc. So let's assume this is A, B, and this is C. Same thing, you go from the centroid to C to bolt C or pin C, and this is RC. And Rn is the bolt of interest, where you're trying to calculate the secondary shear. Okay, so let's take a look at this problem right here. It's a cantilever bracket, and we're applying a load right here of 12 kilonewtons, and of course the problem is telling us to find the factor of safety for the following failure mode, which is the shear of bolts. Right, so as you apply this load, 12 kilonewtons, we're trying to calculate the factor of safety for these bolts in shear. Okay, so first thing, remember from statics, we have to find, you can draw a free body diagram, right, of the bracket. So it looks something like this. And this is not to scale, right? So you have this 12 kilonewtons applied here, and of course you're gonna have 12 kilonewtons applied here to make an equilibrium, and you're gonna have a moment, right? Because it's a cantilever beam or cantilever bracket, so you're gonna have a moment like this. This will make the bracket in equilibrium. Right, so we can draw like a small picture of the bolts to see what is exactly happening. So maybe if I drew the bolts on the next page, we have 3 bolts, right, according to the problem. Let's draw them like this, and they are all equally spaced. Right, 3 bolts, and you have a shear, primary shear. Let's find that one. Usually the easiest one to find, which is just the shear force over the number of bolts, and that's going to be equal to 12 kilonewtons over 3 bolts, and you have 4 kilonewtons. So each bolt will experience 4 kilonewtons, or a primary shear force of 4 kilonewtons. So let's draw that one in a different color. Let's use this one for primary shear. So F prime, F prime, and F prime. Right, and it's equal to 4 kilonewtons. This is your bolt A right here. This is bolt A, this is bolt B, C, or according to the problem, yeah. So let's call it A, B, C. This one is A, this one is B, and this one is C. Okay, so now let's move on to find the secondary shear, which is governed by this equation. The moment times Rn over Ra squared plus Rb squared plus Rc squared, and so on. So for this one, we have to find the centroid, right? Because Ra, Rb, and Rc are the distances from the centroid to the bolt of interest, right? So for this bolt configuration right here, the location of the centroid is going to be in the middle, right? It's going to be exactly at bolt B. So right here. Here's your centroid. right? Imagine just a line, right? A line, and where's the centroid? Is going to be in the middle of that line. So here's your centroid. So no, we don't have to use this long. You could use this one. You could use these two, and you'll end up with the same thing for the location of the centroid. You can. So these two apply. Now for this problem, it's kind of simple, and the centroid is on bolt B. Right. So let's try to find the secondary shear for bolt A, and it's gonna be equal to the moment RA over RA squared plus RB squared plus RC squared. Right, we have 3 bolts. And what is the moment? If we look at our free body diagram, the moment is gonna be the distance from the centroid of the bolt group of bolts to the applied load, right? So the centroid, we said it's gonna be right in the middle of bolt B. So let me use a different color, and it's gonna go all the way to the load, right? And this distance is, according to the problem, is 200 millimeters. Remember, all dimensions in this problem are in millimeters. Right, so let's go back here. The moment is gonna be what, 12,000 Newton times 200 times 10 to the negative 3, trying to convert it to meters. Negative 3 times RA, which is the distance from the centroid G all the way to A. So let's go back, and this distance, according to the problem, is 32 millimeters. So this one is 0.032 meters over RA squared, which is 0.32 meters squared, plus RB. Remember, what is RB? RB is the distance from the centroid of the group of bolts to bolt B, which is basically 0, right? There is no distance. The centroid is exactly on bolt B. So here's 0 squared plus RC squared, and it's the same thing, right? This whole distance from A to C is 64, and from B to A is 32, so from B to C it's also 32 millimeters. So let's go back, and it's gonna be 0.032 squared, and this will end up be, if you plug it in into your calculator, it's gonna be 37.5 kilonewtons. Right, for bolt C, same thing. I'm just gonna write down the formula, and it's gonna be the same exact value, right? Because they're equally spaced from each other. That's why, but let's write down the formula. M, the moment, times RC over RA squared plus RB squared plus RC squared. And remember, this is 0. Right, you plug in the same values, you end up with 37.5 kilonewtons for F double prime C. Right, so you might be wondering, okay, well, we skipped F or the secondary shear on bolt B, but remember the formula. So let's, like a side note here, let's write down the formula for secondary shear for bolt B. M RB RA squared plus RB squared plus RC squared. And we said RB is going to be 0 because there is no distance between the centroid of the group of bolts and bolt B. So this whole thing is 0. So bolt B will not experience a secondary shear. So if you draw the forces like F, remember we drew F prime downward, right? So FA will be in this direction. And there is no F double prime B, it's 0. And F double prime C, this direction. And why I drew the orientation for FA and FC in this direction, if you look at our moment, it's going clockwise, right? So this these bolts should go in a clockwise direction, right? It's the opposite of the moment, action reaction. Right. So okay, moving on. We found F prime and F double prime for each one. Let's find the total F, or the shear force. Let's call this total shear force. Total, it's gonna be the square root, right? We're gonna find the resultant squared plus F secondary shear squared, and this is 4 kilonewtons squared, right? Found F prime to be 4 kilonewtons and F double prime to be, I believe, 37.5 squared. And this, if you plug this into your calculator, you should end up with the value of 37.7 kilonewtons. Good? Yeah. Okay, well, we found the total shear force. What about the stress? Remember, the problem asked to find the factor of safety. And factor of safety, if you remember, is governed by this equation. Sy over the normal stress, but in our case, we're dealing with the shear stress. So from previous chapter, if you remember, we have to convert Sy, this one, to SSY, right? The yield strength in shear. So yield strength in shear over the shear stress. And okay, let's find the shear stress, which is basically the total shear force, right? Total shear force over the area of one bolt. So this one is 37.7 kilonewtons, and the area of one bolt, you can treat it as a circular cross section, so it's basically just pi over 4 times the diameter of the bolt squared. Let me try to make it more clear. Diameter of the bolt squared. And if you look into our problem, for a bolt this size, the diameter is 12 millimeters, right? So for this bolt, it is actually 12 millimeter diameter. And you can also find this from the tables. Okay, so 37.7 kilonewtons over pi over 4. Diameter of the bolt, we said it's 12, so 0.0 0.12 meter squared. This is just units. You will end up with a value for shear of 334 megapascals. Here's your shear. So we found this one. Let's try to find SSY. If you remember from the previous chapter, SSY is equal to 0.577 SY. So it's not quite half of SY, but it's close. So 0.577 times the yield strength of the material. I believe the problem stated that the yield strength of this bracket is 420 megapascals. So you can plug in here 420, and you will end up with a value of 2.34 megapascals. Okay, well, let's use this equation now. Factor of safety is equal to SSY over the shear stress. So SSY is equal to 242.34 over the shear stress was 334, and this will end up to be 0.728, and that is actually, that's your factor of safety, which is less than 1. So you will have a failure in the material. Okay, that concludes our problem. Hope you found this video to be helpful. Thank you. Take care.